Welcome to Sundar's lecture, and in this lecture we are going to see electric circuits, which means uh, we will start from the basics, from Ohm's law, Kirchoff's law, and then we will go to resistors in series, parallel, and we will try to solve the resistor network. We will simplify the bigger resistor network into the equivalent resistors, and then we will go for sources which are connected with the resistors, which means independent sources, dependent sources, and we try to solve problems on electric circuits. First, we will approach the circuits with the conventional methods. Then we will go for nodal voltage analysis method, mesh current analysis method, and then we will go for theorems. And this is the idea of this lecture. So I am going to teach electric circuits. So for that, it is a continuous lectures. We will see many topics. Uh, in the first section, we will see DC circuits, which means we will use only DC sources, and upon DC sources, we will connect resistors and all those kind of elements in the circuits, and we try to get the current in the resistors. So for that, and we will see one by one whatever the things we need to see, and at last we solve gate questions. That is the ultimate aim of this course. So if you follow my lectures, and if you get all the knowledge whatever I am giving through this lecture, then it will be helpful to solve gate questions. That is also we are going to see, right? So first, for that, let us be write this as lecture number 1, right? Lecture number 1. What is this lecture? This is electric circuits. Electric circuits. And in electric circuits, first we will see DC circuits, only DC circuits, right? Right. Now, before seeing DC circuits, we need to know certain basic laws. In that, first we will see Ohm's law. So what is Ohm's law and what it actually explaining us? At constant temperature, this is very important. At constant temperature, current is directly proportional to directly proportional to voltage. That's all. This is the Ohm's law, which means what this actually telling us, V is directly proportional to I. That's all, right? Since you see here, you can clearly see that at a constant temperature, if temperature is constant, then resistance in the circuit will also be constant, right? That is the constant temperature uses, um, which means the resistors will be also constant. So if you want to take this directly proportional symbol, then we can multiply the I with some constant, and that constant which is nothing but this resistor, right? So we can directly write V is equal to I into R. That's all. This is the basic formula you need to know. That's all. If you know this formula, it is enough to solve all the circuits. Every electrical circuit should follow Ohm's law, right? Now, second law, that is nothing but Kirchoff's law. Kirchoff's law. So, Kirchoff's law, it has two laws. First one, Kirchoff's current law. Kirchoff's current law, right? So before knowing what is Kirchoff's current law, you should know what is a node, right? So you see, in electric circuit, if I consider a node, you see this, I will draw the diagram first. This is branch number 1, this is branch number 2, this is branch number 3, right? In an electrical network, if you see any branches, that means 3 or more branches connecting at a particular junction, 3 or more branches connecting at a particular junction, we call this junction as node. We call this junction as node, right? So what is node? What is node? That you have to understand. 3 or more branches connected at a junction. That's all. This is what node, right? So if you know what is node, then it is simple to understand what is Kirchoff's current law. What is Kirchoff's current law? It is very easy. You see, I take a node now. So I have connected a node. So I'm just drawing the branches. There are several branches connected. Let us assume that there are several branches are connected like this. And every branches, there is a current in every branches. And I am just drawing the current direction. Right. So this is the diagram that this is node now, right? This node carrying 6 branches, and 6 branches has 6 different currents. And what is Kirchoff's law explaining as? I'm just writing this, then I will tell you the exact expression for this. Sum of current flowing towards the node is equal to sum of the current flowing away from the node. So this is the definition, and now you see, I will explain this. Sum of the current flowing towards the node, right? This is my node, and you see this. I will just try to explain you in a way that if you want to explain, or if you want to know what is Kirchoff's current law, first you put equal to symbol. First you put equal to symbol and see this node now. And right, I will take this node as A, node A, right? I will write here also at node A. I'm just applying Kirchoff's current law, right? Now you see at node A, first you see current I1. I1 is going away from the node. This is going away, right? This is going away from the node. So what you do, you put that whatever the current is going away from the node, you put it in the right hand side. This will be I1, right? And you see I2 also flowing away from the node. It is going from the node, away from the node. So you have to put that also in the right hand side. And you see I3 also flowing away from the node, right? It is going away from the node, right? So you put this is plus I3, and you see now I4 is going towards the node, So what you do, you put in the left hand side, right? Whatever the current is flowing towards the node, you put it in the left hand side. Whatever the current is flowing away from the node, you put it in the right hand side. That you have to add all the currents, right? Then you see I5. I5 is also what? It is going away from the node, right? It is going away from the node. So you put in the right hand side, and you see I6. I6 is also going away from the node. That you put here, it is plus I6. So this is the Kirchoff's current law. So you try to understand, sum of the current flowing towards the node will be equal to sum of the current flowing away from the node. So this is the Kirchoff's current law. Right? We will take a new page. Fine. Next we take Kirchoff's voltage law. So this is number 2. So we will take Kirchoff's voltage law. Kirchoff's voltage law. So this is nothing but KVL. We always use this KVL again and again, right? So next we will take a circuit now. So I am just drawing the circuit to explain Kirchoff's voltage law. A voltage source, and there are resistance connected, right? This is the resistance, and we will mark these things. So this is V, and this is R1, this is R2. And you try to understand, one thing is very important. Kirchoff's voltage law is applicable only in the closed path. And now you see here, this is a closed path. You can see this is a closed path, right? If there is a closed path, then obviously there will be some current flowing. So what we will do, we will assume the current direction like this. Right? I want to tell you one thing. This current direction will be assumed by us. Wherever we see this, we will assume this, and then we try to solve the problem. If the value of the current is negative, then we can reverse the direction. Unless then, the current direction can be assumed in any way. Maybe it is in clockwise direction, or it may be an anti-clockwise direction. You don't need to worry about that. Fine. Now we have assumed the current direction, and this is I, and the current flowing through this resistor will be also I. Fine. Since it is a series path, then both the resistor will carry the same current, right? So now I will write down the definition, then I will tell you what is the Kirchoff's voltage law. So sum of the potential rises is equal to sum of the potential drops. That's all. This is the definition for Kirchoff's voltage law. Sum of the potential rises will be equal to sum of the potential drops. And now you see, you have to see in a circuit which are all the potential rises and which are all the potential drops. That I want to explain you two things. One, you see, you see the current direction in if it is a voltage source, or if it is maybe any other elements in the circuit, you see the current direction. If the current direction is from minus to plus, then that will be potential rises, or that element is delivering power to the network, which means you see this is the voltage source. You see the current is flowing from minus to plus, right? If the current is flowing from minus to plus, then you have to clearly understand that this voltage is a potential rise. So minus to plus. So you put equal to symbol. So here you see, if it is a potential rise, you put it in the left hand side. And now you need to see which are all the things it is potential drops. And now you see, if you want to see, if you take a resistor always drops the voltage, or it will absorb the power. That you have to clearly understand, right? So always a resistor will be like this. This will be positive terminal, this will be negative terminal in the resistor. Current will always enter from plus and it always leaves from minus. That you have to understand. This is default thing, right? So this is plus, and so you see in this resistor, this is plus and this will be minus. And I want to ask you, what is the voltage drop in this resistor by Kirchoff's law? What is the formula for voltage? V into I, right? So here voltage drop across this resistor, I am just taking it as V1, and what is the potential drop across this resistor, and I will take that as V2. That's all, right? So this is V1, this is V2. Now I just write down the potential drops in the right hand side. You see this equal to symbol, write all the potential rises in the left hand side, write all the potential drops in the right hand side. So here you see this will be V1 plus V2. That's all. So this is the expression. Now you see this V is V, nothing but this is V, which is equal to, what is V1? What is V1? Voltage. I into R1. So here you write I into R1 plus, what is V2? V2, it is I into V2, it is I into R2. So you write here I into R2. That's all. So this is the final expression for Kirchoff's voltage law in this loop, in this closed path, or it will be considered as loop, right? Now, one thing I want to explain you again, I will not always write Kirchoff's voltage law in this way. No, I never. Since students may confuse which is potential rises, which is potential drop. In some circuits, even voltage source will act as a potential drops. The current will flow from plus to minus in a voltage source. If you have two voltage sources in a loop, higher voltages, higher value voltage sources will be delivering the power, but lower value voltage sources will absorb the power. So students will confuse that. So I don't write expressions like this. Fine. I just want to tell you, with the same circuit, I will explain you how I will write the expressions for KVL, only KVL. So this is the circuit, right? Whatever the circuit you see, I will take it again so that you can easily understand. You can easily compare. Both the final answer will be same. There is no difference in the final answer. You don't worry about that. So this is plus minus V. So this will be R1. This will be R2. Now you see, if you see any closed path, I already told you there will be some current flowing, right? So if it is a closed path, then assume your current direction, this is I, right? Now you write down the current directions in all the resistors. So in this direction, the current is actually flowing. So I have drawn arrow mark like this, and in this direction, right? This is coming from upper side to lower side. So your current value will be drawn like this. So right now you see KVL has to be written for a closed path, right? So start from this point, go in this way and come to this point, end up with that, end there, right? So you see, first I will start this point, then I will go in this way. If I travel from minus to plus in a voltage source, if I travel from minus to plus, you put plus symbol, and whatever the voltage value you take it as V. Whatever the voltage, if it is 5 volt, then you put 5 here, that's all, right? Then you go in this direction, come here. Why I have to travel in this direction? Since my current I have assumed in clockwise direction. If I assumed it in the anti-clockwise direction, then I have to start from here, go in this direction, come here, then I have to end up with this point. But since I have assumed in the clockwise direction, I am moving in the clockwise direction, right? So you go here, I have marked the current direction here, I am also traveling the same direction, right? If I am traveling in the same direction, then you put minus symbol, then you write down the voltage there, write down the voltage at that point. So what is the voltage? I into R1, I, because what is voltage formula? V into I into R, right? So I into R1. Then you come here again, the I'm going in the direction, clockwise direction, this current is also in the same direction. So what you put here, again you have to put a minus sign, and what is the voltage there? I into R2, right? Now you see you have ended here, where you have started, right? At the same point. Now you put equal to 0. That's all. This is the expression for KVL. Now you see, you see this expression, both are same. You bring IR1 minus IR2 to the right hand side, then you will get the same expression. So this is how we will write down the KVL expressions hereafter, right? So you try to understand that one very clearly. Fine. Right, now we will take a numerical example so that you can easily understand. Example, let us we take any circuit with the two loops. Now you see I will draw like this. With the two loops, I have drawn a circuit like this, and we will assume this is plus minus V1, this is R1, this is R2, this is R3, then this will be plus minus V2, right? So now this is the circuit we have taken. Now you see there are two loops, there are two closed paths. So obviously what you have to do, you have to assume two different currents are available now. So this is I1, and what is this? This will be I2. Now you have two different KVL expressions. You will have two different KVL expressions. First, you draw current directions, then you mark the currents in the all resistors, right? So now you see current, I will take a different color. So current in this resistor, which means I have assumed I1 like this. So in this resistor, I1 is flowing. So you put I1 and you come in the same direction, and you see this resistor. In this resistor, I1 is flowing from the top to bottom. So you just draw like this. This is I1, and that's all right. Only two I1s are there. I have marked two things, and then you go for I2. So I2 is flowing in this direction. So in this resistor, it is from bottom to top, the direction of the current. So this will be I2. Then you go in the same direction. Then you see here, there I2 is flowing. So you put this is I2, and that's all right. You don't need to put the current directions in voltage sources. That is not necessary because we are going to write the voltage expression. So this is obviously not necessary. So now you write down the KVL expressions, right? So if you want to write the KVL expression for the first loop, first loop, first loop. So now you see, start from this point and end with this point again, right? So from here you go, I am going in, you have to travel in the I1 direction. So you go in this direction, from minus to plus I am moving. So what I have to do, I have to put plus V1. Then you see I'm going in the same direction. I'm going in the clockwise direction. This I1 is also in the same direction. What you have to put there? You have to put minus I1 R1. Then you see I'm going in the same direction, in this direction. Again this current is in the same direction. So what you have to put here? Minus I2 I1 R2. Then you see here I am coming in this direction, but this current is in opposite direction, right? So if it is opposite direction, then obviously you put plus I2 into R2. Then you see I have ended here. So at last you put equal to 0, right? This is the first one. Then for the second loop, so start from this point, go in this direction and come here again, right? So from this point I'm going in the same direction as I2. So you have to put minus I2 into R2. Then I am going in this direction, but this I1 is coming opposite to me. So what I have to do, I have to put plus I1 into R2. Then I am going in the same direction as I2. So what I have to put here? This has to be minus I2 into R3. Then you come here. Now you see I have to travel in this direction. Now current is traveling from plus to minus. I have to travel from plus to minus to this point, right? So this has to be written. This has to be written minus V2. That is why I'm telling you from the beginning, since there is a confusion here. So now it is very clear, right? So I am traveling from plus to minus, so I have to put minus V2. I have ended up where I have started, right? So what this becomes now? This expression becomes 0. That's all. So this is the KVL expression, right? Thank you. We will continue in the next class.